In the previous sessions, we discussed how we can find the enzyme parameters Vmax, Km, and Vmax over Km from experimental data. So we take different substrate concentrations and we then measure the initial rates that correspond to the individual substrate concentrations. And we decided, or we discovered, that usually a Michaelis-Menten plot, where we just simply plot the substrate concentration against the rate, where we get something like that, is very often not a very good idea, because we just simply can't very well estimate our Vmax. So where is Vmax? Does it end up here, or does it go up here, or something like that? So, and if we can't get Vmax, we can't get half of Vmax, and we can't get Km. So a Michaelis-Menten plot should not be used really to analyze experimental data. So instead, what we said, we could perhaps use a Lineweaver-Burk plot or a double reciprocal plot, where we plot the 1 over the rate versus 1 over the substrate concentration, and we would usually get hopefully a straight line. This point here would be 1 over Vmax. The gradient would be minus Km, would be plus Km over Vmax. And the x-intercept would be minus 1 over Km. Now, that's all nice, and we get the data, but we also said that the Lineweaver-Burk plot comes with some problems. One of the problems is that we get all our data as the inverse, because it is a double reciprocal plot, and we have to inverse the inverse again. And the other problem with the Lineweaver-Burk plot is it is statistically not very good, because we've got some data bunching. We've got data crowding in that area, and then we've got some influential points up here. And from a statistical point of view, this is quite problematic, because we give data different weights when we put in this straight line. And that can be quite problematic. Also, if the values for Vmax are quite large, then the inverse would be very small. So we would get lines down here, and we can imagine that sometimes we even get, just simply because of the line of best fit, we might even get a negative line, or a line through a negative 1 over Vmax, which of course doesn't make a lot of sense. So a Lineweaver-Burk plot is marginally better than a Michaelis-Menten plot, but it comes with statistical problems. I also discussed with you that we could use an Eadie-Hofstee plot, where we plot the rate versus V over S, and we would get something like this. We don't have the issue with the statistical problems. We don't have the issue with the inverse numbers, because this y-intercept actually is Vmax. Here we get Vmax over Km. And the gradient for this would be negative Km. So that's great. But the problem with an Eadie-Hofstee plot is that we do something that is a bit frowned upon, because while we have on the y-axis, we have our dependent variable. So y is the dependent variable. On the x-axis, we plot a mixture of the dependent and the independent variable. The independent variable is the variable that we have control over. And we really should only plot the independent variable and not a mixture. And that's why a lot of people don't like this plot. because it is problematic. You mix something that you really shouldn't mix. So the question is, can we do something slightly better? And in fact, there is an answer to that, and that was developed by Eisenthal and Cornish-Bowden. They actually developed what is called an Eisenthal Cornish-Bowden plot or direct linear plot. Direct linear plot. Now, how does that work? Well, they started off with the Michaelis-Menten equation, V equals Vmax times S over Km plus S. That's the usual starting point. They divided the both sides by S, so we get V over S equals Vmax over Km plus S. And then we bring the denominator to the other side, and we end up with V over S times Km plus S equals Vmax. Now, of course, we can multiply into the bracket, and we would get V over S times Km plus V over S times S equals Vmax. And we see that the S cancels out, and we can write that in a slightly different format. We can write this as Vmax equals V over S times Km plus V. So that is how we would write that. Now, what have we gained from that? Now, Cornish-Bowden and Eisenthal actually said, why don't we just simply plot Vmax and Km? Now, this is a little bit weird, because before we would have plotted V over S and V, or S over V. So that was sort of quite strange. So we would plot something like we plot Vmax versus Km. But actually, we don't have these numbers, do we? This is actually what we are looking for. But what we do know in this case is that we already know the y-intercept, because if we are looking at it, it is y equals mx plus c. So our y-intercept would be the value of v. So if we pick, for example, here the first value of 20 micromolar, so this would be our first value for v. Now, what would be, so we would like to put a line through that somehow. So ideally we would have a line, and I should not delete it. I should actually write this properly. So we want a nice line, so that is our V here. Now, what is this point here? How can we find this point? Because we need these 2 points for this line. And what we can do is a little bit of algebraic trickery. We just simply say, well, this point, this x-intercept, is just simply if our Vmax equals 0. So Vmax equals 0. So what have we got then? We would have 0 equals mx plus c. And now we need to solve this equation for x, and that is pretty easy. We get the c to the other side and divide by m. So x, this point here, x would be minus c over m. Or if we put that into our equation here, we would get x equals minus c, that is minus v, that is our rate, divided by the gradient, that is v over s. And if we just use basic algebra, we find that this point here, this x, this point here, would be negative s, the negative substrate concentration. So here we have minus S1, that is the corresponding substrate concentration. So here we have 20 and minus negative 5. So that gives us a nice sort of idea how we can do this plot. So what we see here, and here I've done it with the proper numbers, what we see here is that, for example, if we use a substrate concentration of 100, then we get negative 100 here, that's our substrate concentration. And this point here would be the corresponding rate. So if we have a look at it again, here we've got negative 100, that is the substrate concentration, equals negative S. Whereas this point here is our V, and that was, what have we got at 183.3. 83.3 micromolar per minute. So we've got a line, and what we know is that our values for Vmax and Km must be on this line, because that is what this equation basically tells us here. That is what the equation says. So, of course, we have two unknowns. We have Vmax and Km as an unknown, and therefore we don't know where Vmax and Km is. But we can figure that out very easily, because if we take another value for S and V, so if we, for example, take, let's say, 20, so 20, and corresponding value of 50. So we can draw another line here. So here that was our original line with 100 and the corresponding value, and here we've got 20 and the corresponding value. And where these two lines meet, that is actually the value for Vmax and Km. So we get, for Vmax, we get this value here, and for Km, we get this value here. So that would be our Km that we defined from the first and the second line. So that would be here. So we would say our Vmax here for this first set of data, where we compare 100 and 20, and Km of 120 as well. So we can do that quite nicely, and we've got a really nice estimate already for our data. And of course we can do that for all the substrate concentrations that we have, and we would get something like that. So here we've got the different substrate concentrations, the different values for the substrate concentrations, plotted as in the negative range, and the corresponding values for the rates. So here we've got the substrate concentrations, or rather the negative substrate concentrations, and we see that the points all intersect in more or less one point. And if we take this where they meet, that is Vmax. That is our Vmax value. And the corresponding is probably somewhere here. Not drawn very nicely. Say that would be our Km of 20. So this is basically how we can apply this plot quite nicely, and where we use these lines of S and V, and they are direct lines, they are the direct linear representations of the substrate and initial velocity, initial rate pairs. And we can nicely plot that. Now, the really great thing about this linear plot is there is no problem with the statistics because we don't do anything weird. And the massive power of this plot comes when we have noisy data. What do I mean by noisy data? Here is a similar data set like we had before, but this time the data have a little bit of experimental variation. And if we plot these data as a Michaelis-Menten plot, for example, what we see is that, yeah, we get a sort of a smooth curve, but we also see that the data points are not necessarily all on this line here that is representative for the Michaelis-Menten. And we still, of course, can't determine our Km, or because we don't know exactly where Vmax is. But this time we have the additional problem that we have experimental uncertainties, experimental errors, and things like that. Now, how does the direct linear plot deal with it? Well, we deal with it by just simply plotting these different combinations of the substrate and initial rates. And what we get is something like that. So it's no longer nicely in one plot and one point that all the lines converge to. We have several intercepts here, lots and lots of these lines that cross each other. Now, what does it mean if these lines cross? If a line crosses, it means that this is a value for Vmax and Km. So for these two here, if we compare these two data sets here, we would find the corresponding Vmax here and Km here. But if we compare this data set here with, let's say, this data set, then we would get a Vmax of this and Km of this. So in a way, what we will get is for each combination of the S and the initial rate, for each combination, we get a separate Vmax and Km. So each combination of data pairs gives a separate estimate for Vmax and Km. How many of these combinations can we do? Actually, we can calculate that. The number of combinations that we get would be the number of data observations that we have, the number of substrate concentrations times, if we call that n, times n minus 1 divided by 2. That's the number of crosses that we basically get. That's the number of Vmax and Km that we get. And so if we've got, say, how many did we have here? we had 1, 2, 3, 4, 5, 6, 7. So we would get 7 times 6 divided by 2. So we would get 21 different Vmax and Kms. And now what we can do is we can say we've got Km1, Km2, and so on and so forth until Km21. And we have also Vmax1, Vmax2, and so on until Vmax21. And what we can do now is we can actually do a little bit of statistics with it, and we can say, right, what would be the median? And we would go for the median for Km. The median, because we might even have some negative values here, which we actually should disregard, because we can't have a negative negative Km. So we would not use the mean for that, but we would do the median for it. And likewise, we would calculate the median for our Vmaxes that we have. And this would be actually a very good and statistically sound estimate for Km and Vmax. So with this direct linear plot, it allows us actually to do proper statistics, because we get a set of data for our Km and Vmax. We don't just simply have a single data set like we've got with, for example, a Lineweaver-Burk plot or with an Eddy-Hofstee plot. We get a number of data sets, and for that we can determine a nice median for these data. In terms of plotting, again, we don't need to do a lot of calculations. In fact, we don't need to do any calculations. We just plot directly the negative substrate concentrations versus the corresponding initial rates, and we get a number of lines, and from that we get these data sets and we can find out the median. So this is why this direct linear plot, or Eisenthal Cornish-Bowden plot, is really a very, very useful tool. And of course, if you've got sort of lots and lots of data points, then you get lots and lots and lots of data, which makes it a little bit awkward. I think that is probably why people don't like it, because you get so many data. But from a statistical point of view, that is really an excellent way of dealing with enzyme data, and I think it is very underappreciated, this really ingenious plot that allows you to very nicely calculate Km and Vmax from even quite noisy data. And that is a huge advantage. So I hope this makes sense, and thank you very much for watching.